Hello, my name is Noel McWilliam. I'm Director of Mitra Vitae. I'm going to guide you through a simple three-step calculation demonstrating how to use the sun's energy in desert regions to produce clean water that can be used to harvest even more energy from the sun. I'll prove how 1 unit of energy invested in water production can yield more than 1 unit of energy from the crop produced. Billions of dollars have been spent on nuclear fusion since the 1950s for this purpose only, to create a reaction that yields more energy than the process consumes. Fusion technologies are unlikely to be ready within the next decade. Fortunately, this same effect is possible by emulating nature to tap into the vast solar potential of the world's deserts. Let's begin our story in the Sahara. At high noon, each square meter receives almost 1,000 watts of energy, equivalent to 10 100-watt light bulbs. Over the course of a year, the Sahara receives 2,700 kilowatt hours of energy per square meter. Let's Google that. Now, we could install solar panels and transmit this power to more hospitable locations. But let's explore what happens if we invest energy in water production and then use this water to grow a biofuel crop. Is it even possible to get more energy out of the crop than we invested initially? To keep things simple, let's not consider specific technologies and their various efficiencies, but first ask what the theoretical maximum output is per unit input. There are 3 steps to this simplified calculation. Step 1. Calculate the amount of water we can produce. Step 2. Calculate the area of land we can irrigate with this water. Step 3. Calculate the amount of energy available within the crop grown on this land. Let's take a look at step 1. Removing salt from seawater takes energy to break the bonds that attract the water molecules and the ions in the salt. The energy needed to produce 1 cubic meter of fresh water is called the specific energy of separation. Therefore, the volume of water we can produce from our 1 square meter of Saharan desert will be 2,700 divided by the specific energy of separation. We want to know the maximum output of water we can produce, so let's Google it. Right, so the maximum volume of water we can produce is 2,700 divided by 0.706 kilowatt hours per cubic meter, which is equal to 3,800 cubic meters of fresh water. Not bad. We want to use this water for irrigation. So in step 2, we want to find out the maximum amount of land on which we can grow an irrigated crop. Firstly, how much water does a crop need in a climate like this? Well, wheat production in Australia is totally reliant on rainfall. So for the purpose of this simple calculation, let's assume we top up the Saharan rainfall with irrigation to achieve the same overall level of water in the Australian wheat belt. Back to Google. The annual average rainfall in the wheat belt is around 328 millimeters, but in the Sahara it's about 100, so we'll need to top up to 228 millimeters of water. Remember, we know the volume of water, and we now know the depth of irrigation required. The area we can irrigate to a depth of 228 millimeters is therefore 3,800 meters squared divided by 0.228 meters, being careful of units, which is 16,700 meters squared, around 1.6 hectares. Now, the final step. What's the maximum amount of energy we can extract from the irrigated crop? We already know the amount of energy the crop is receiving each year, 2,700 kilowatt hours per square meter. So the total amount received is 2,700 times by the area, 16,700. We'll need to find out how much of this energy is actually contained in the above ground biomass. So let's check Google. The maximum conversion efficiency from solar to biomass is 4.6%. Multiplying out, the crop yields 208,300 kilowatt hours per year. That's 770 times the original input. We could reinvest this output energy back into our process, yielding 770 times our prior output, which itself is 770 times our original input energy. Iterating again and again, it wouldn't take too long before the entire desert were green. I hope these calculations demonstrate the potential for this new approach and the need to urgently research these systems not only as a way to generate clean fossil-free power, but also as a means to capture carbon by enriching soils with organic matter from plant roots and residues. Of course, another important and pressing question is whether these systems have immediate practical use in energy production and the fight against climate change. The calculations are somewhat more involved and will depend on the efficiencies of the specific types of technologies used. The actual yield is a function of crop irrigation, soil type, the type and timing of irrigation, harvesting method, the method of generating biofuels from crops and their residues, and the conversion of these fuels back into energy. Our initial estimates place the currently attainable gain between 0.5 and 11, depending on the specific combination of technology, crop, soil, and climate. Although much less than 770, we only need to be above 1 to green a desert. Try multiplying 3 by 3 and 3 again and again and again, and see how quickly you break your calculator. Thank you.